Good morning. This is our first lecture into the mechanics of materials. Once again, we're using the R.C. Hibbeler text. This is the 5th edition. Pearson version. So we'll begin our studies into chapter 7, entitled Stress and Strain. And here we will use some of the concepts we learned in our statics semester, forces, moments, method of sections, method of joints, all the techniques we learned in our study of statics. To start working through the internal effects of loadings. So mechanics of materials is defined as a study of the internal effects of stress and strain, which are two terms we will define and work through pretty soon, in a body that is subjected to external loadings. Stress is associated with the strength of the material, while strain, we'll say, measures deformation of a body. So since we're dealing with, say, internal effects of these external loadings, we have to have an understanding of what forces we have to account for. So we look at figure 7-1 from the text. In order to see the internal loadings acting on a specific region of a body, a cut or section has to be made. The free body diagram of one of these section parts will show the applicable forces. So if we were to cut a body, this is where the cut was made. And this is the surface area, otherwise known as cross section. Keyword here is section, where you made this section across the area. At a point O, and O is typically taken at the centroid, so always assume the point O is at the centroid of the area, unless otherwise stated. So then we can find the resultant force and moments of the internal loadings at this point O. So there are 4 different types we'll say of resultant loadings. Let's draw the shape again. So once again, I'm redrawing the shape of the section area. This is where the cut was made. We'll cut out point O. So at this point O, we have let me just show it. So we can see surface area cross section. We have a shear force we have a normal force we have a bending moment, and we'll define all these terms in a few seconds. And we have a torque or torsional moment. So the normal force, abbreviated as N, uppercase N, is defined as the force that acts perpendicular So at 90 degrees to the, say, surface area. And it's developed where the external loads tend to push or pull on the two segments of the body. Your shear force, uppercase V, this lies in the plane of the area, the surface area. You have your torque. This is developed when external loads tend to twist one segment of the body with respect to the other, about an axis perpendicular to the area. And last, we have the bending moment. This is caused by the external loads that tend to bend the body about an axis So what we're talking about is external forces can cause certain internal reactions within the body. It can cause a shearing effect, a bending effect, a twisting effect, etc. And that's what we're concerned about in our analysis of materials. How do we evaluate what materials can withstand certain loads in addition to our study of from statics, where we have to deal with external loads from a, say, support perspective? Now we're taking that analysis further to understand internally what materials are best for what jobs. Now, in coplanar loadings, and I'll draw a body for you. Once again, is our point O. Normal to this surface. You have a shearing force, and you have your bending moment. So for coplanar loadings, we only have to evaluate our normal force, our shear force, and our bending moment. Simplifies it quite a bit. So let's get some practical analysis into what kind of problem set we're dealing with here. So let's look at example 7.1 in the text. This is on page 316. Here, they want us to determine the resultant internal loadings acting on the cross section at point C in the given figure, which is a cantilevered beam. So just to reproduce, we have a beam which is supported here at A. We have a distributed loading. Our point C here is a distance 3 meters from the wall and 6 meters from the end at point B. So we want to know the resultant internal loadings at the cross section at C, which means we have to make a cut at C. So if we make the cut at C, we'll be left with two segments. We can have a segment AC or a segment, call it CB. And this is a cantilevered support where the point at A has all our support reactions. So if we did AC, then we have to figure out our support reactions at A. However, CB will allow us to solve the problem and not have to do the external support reaction analysis. So if we deal with segment CB, then the problem becomes a lot easier and simpler. Okay, so reproducing the free body diagram after making the cut at C, let's go to a fresh page. This is after making the section at C. So first thing first, we have to, this is coplanar analysis, so we have to account for our internal loading, so our normal force at C, our shearing force at C, and our bending moment at C. These are our three unknowns we have to solve for, and what the question is asking for, the resulting internal loadings. So we also have to account for the intensity of the distributed loading. So initially, back to our statics analysis, this is a quick review. The intensity was 270 newtons per meters. It's a triangular loading for 9 meters. But since we sectioned it at C, we're left with 6 meters. So our loading is smaller. So what's our intensity here? Solve for X. So our new loading intensity for the triangular distributed loading is 180 newtons per meters. And this distance here is 6 meters. So we know then we have to replace the distributed loading with its equivalent resultant force. And we know the magnitude of the resultant force is equal to the area under the loading curve. We'll say equal to area under loading curve. Since this is triangular, be 1/2 the base times the height. 1/2 the base, 6 meters, times the height, 100, or intensity, 180 newtons per meter. So my equivalent resultant force is 540 newtons. Remember, this acts at the centroid. So if this length is 6 meters, this resultant force (2 meters from the point C is where it acts. Now, as a brush up, these formulas, etc., can be found in our Appendix B on page 815 in the text for a triangular where the centroid is located in the area. Let's go to fresh page. Reproduce that. So redrawing our beam in question, this is point B, point C, and our normal force, our shear force, and our bending moment. We found our resultant force from the loading. This is 4 meters, and that's 2 meters. So now we can begin working and solving the problem. Our equilibrium equations apply. So the sum of our forces in the x direction, we only have one, our normal force at C. And it's in the negative x direction. The sense of the vector is in the negative x direction. So it'll be negative NC equals 0. So we've solved for one of the internal loadings. The shear force, V sub C, is the direction of that is oriented in the positive y direction. So you have V sub C minus the 540 newtons. So now we have to solve for our last unknown internal loading, which would be the bending moment at C. So to do that, we need to take the sum of all our moments at point C, which is another one of our equilibrium equations. So the sum of all our moments at point C must be equal to 0 for equilibrium. So this case, remember, counterclockwise direction is positive, clockwise is negative. So MC in this case is negative. The 540 Newton force, which is separated by a distance of 2 meters from point C, is causing a clockwise, so negative rotation about the point C. solve this out. The bending moment at C is equivalent to negative 1080 Newton meters. So this indicates that the bending moment at C is actually acting opposite the direction we've oriented in our free body diagram. So in conclusion, we've solved the three unknowns: normal force, shearing force, and moment. Let's take a look at some problems from the book so we can get a clear picture of what is being asked in this chapter. Let's take a look at problem 7-1. This is on page 322 in the text. So we have a shaft that's supported by a smooth thrust bearing at B, a journal bearing at C, and they want to know the resulting internal loadings on the cross section at E. So here we have to go back to our chapter 4 study. Turn to page 186 and 187. So B is a thrust bearing. So we go to chapter 4. This is page 186 through 187 for our support reaction table. This is table 4-2. So B is a thrust bearing. And a journal bearing at C. So for journal bearing, the reactions are 2 force and 2 couple moments. But we can ignore the couple moments if the body is supported elsewhere. And please note this is in 3D, this table 4-2. And for the thrust bearing, there are 3 force and 2 couple moments, but once again, we can ignore the couple moments. So here we're working in 2D space from the problem set we're working now. So to draw the figure out as a free diagram space, let's start with our shaft. We have the 400-pound force here. We have the 800-pound force here. At B, which was the journal bearing, I'm sorry, B was the thrust bearing. We have to account for our X and Y components. So BX and By. C, the journal bearing, just have to account for our vertical support. And E is right here where we'll make our cut. Because that's what the problem is asking. The cross section at E, so we have this section at E. So looking at this, we can deal with either section, and this is point C, this is point B, this is point A, this is point D. We can deal with section AE and have to deal with more unknowns than if we dealt with section ED. So let's deal with section ED. But we still have to determine the support reaction CY. So then if we take the moment about a point, we can ignore the forces that interact at that point. So if we take the moment about point B using our equilibrium equations, we can ignore By and Bx because there's no perpendicular distance from their lines of action about point B, because the lines of action go through point B. So we take the moment about point B. CY causes counterclockwise, so positive rotation. Perpendicular distance to point B is 8 feet. The 800 force causes a negative rotation about point B. Perpendicular distance to point B is 12 feet. And the 400-pound force causes positive counterclockwise rotation about point B and is separated by a distance of 4 feet. Set it equals 0. Solve for our CY. That's 1,000-pound force. Go to a fresh page. So we will be dealing with segment, call it ED. So we have our CY that we just calculated to be 1,000-pound force. We have our 800. Coming in the negative Y direction. This distance here between CY and 800 is 4 feet. So at point E, where we made our section, remember the question is asking about the internal loadings. This is coplanar, so we have to account for our normal first, which is perpendicular to the cross section. Our shearing force, which acts in the plane of the cross section area, and our bending moment. Those are our three unknowns. So then using our equations of equilibrium, sum of forces in the x direction equal to 0. We have our negative NE, since the orientation of the sense of that vector is in the negative x direction. For our y component, sum of our forces in the y direction equal to 0. We have our VE plus our 1,000-pound force minus our 800-pound force. And for our bending moment, we take the sum of all our moments acting at point E. So the 1,000-pound force causes counterclockwise, which is positive rotation about point E. The perpendicular distance there is 4 feet. The 800-pound force causes clockwise, so negative rotation. Perpendicular distance there is 8 feet. And we have to account for our bending moment M sub E. Solving for the bending moment, 2,400-pound force feet. So we solve for the three unknowns, and the negative signs on the V sub E and M sub E indicate that they act in the opposite sense to what is shown in our diagram. Let's take a look at another problem. Let's look at 7.4, same page. Once again, we have a shaft. Supported by a smooth thrust bearing at A. So similar to the problem we just worked. And a smooth journal bearing at B. And this time we have a distributed loading across point C. And they want us to determine the resultant internal loadings acting on the cross section at C. The loading diagram is a rectangle, so it can be represented by a resultant force equal to the area under the curve, which is base times height. So let's replace and draw a free body diagram. A was a thrust bearing, so from our table 4.2, we know that has a AY and an AX component, something that we just worked in the previous problem. We have a 900-pound force here. 900 Newton force here. B is a smooth journal bearing, so we have the BY. This is the resultant force here. Is base times height. (600 newtons per meter) times 2 meters. (1,200 newtons). So if we section it at C, and this is point C, then if we work the segment, say CD, that's less unknowns than if we work segment AC. But we still have to determine the support reaction BY. So we take some of the moments about point A, we can eliminate having to solve for AY and AX. So then our BY causes counterclockwise rotation about point A, and that's separated, separated by a distance of 4.5 meters. Our resultant force from the loading causes clockwise, so negative. and that's separated by a distance of 2 meters from point A. And the 900-pound force, Newton force, is separated by a distance of 6 meters. Solving for By, so now we can redraw our free body diagram on segment CD. We have our normal force at C, shear force, and our bending moment. So now that we made this section at C, we have to take account the change in the loading base. So the intensity is still the same, 600 newtons per meter, but the base length is no longer 2 meters, it is 1 meter. Which means the resultant force now, base times height, is 600 times 1, so 600 newtons, and it acts .5 meters away from point C. So let's redraw this on a fresh page here. We have our 900 Newton force, the 1733 newtons we calculated from B sub Y. We have our resultant force from the distributed loading. This distance here is 0.5 meters now. We said this is 600 newtons. This distance here is 1.5. And this distance here is 2. Our normal force at C, our shearing force, and our bending moment. Those are the unknown internal loadings we have to solve for. So using our equations of equilibrium, sum of our forces in the x direction, N sub C, our normal force is 0. Sum of our forces in the y direction, you got V sub C minus our 600 newtons plus our 1733.3 newtons minus our 900 newton equal to 0. V sub C to solve for our bending moment, we'll take the sum of all our moments about point C. This gives you the 1733.3 Newton, which is separated by a distance of 2.5 meters. The 900 Newton force causes a negative rotation about point C, separated by a distance of 4 meters to point C. The 600 Newton force causes a negative rotation about point C. And we have to account for a bending moment. Solve for M sub C. (433 Newton meters). And with the negative value for V sub C, we know that the shearing force acts in the opposite sense to what is shown. Take a look at another problem. Problem 7-8 on page 323. So the beam supports the distributed loading. Determine the resultant internal loadings acting on the cross section at point C, and assume the reactions at the supports A and B are vertical. So let's draw our free body diagram. So vertical, this is just a BY component, just an AY component. This is a triangular loading. So we know the resultant force acts here equal to the area under the curve. So that's 1/2 the base, which is 6 meters, times the intensity here, which is 4 kilonewtons per meter. So it's 12 kilonewtons. The distance here is 2 meters, 1/3 from the end. So to figure out support reactions, if we take the sum of the moments about point A, counterclockwise rotation being positive, you have BY times 6 meters minus the resultant force from the distributed loading. So it's 12 kilonewtons times 2 meters BY is 4 kilonewtons. So now the problem asks us to solve for the internal loadings at point C. So we have to make a cut there, which is 1.5 away from point A. So redrawing. You have your BY, which we know is now 4 kilonewtons. Which is solve for our new loading. So the intensity of the triangular loading was 4 kilonewtons per meter when the base was 6 meters. Now that our base is 4.5 meters. What's our new intensity? It's 3 kilonewtons per meter. This base length is 4.5 meters. The equivalent resultant force from this loading is 1/2 the base times the height. .75 kilonewtons. And it acts 1.5 meters away. This distance here is 1.5 meters. Since we made the cut at C, we have to account for our normal force, our shearing force, and our bending moment. So let's redraw this on a clean page. We have our BY support reaction, which is 4 kilonewtons. We know our resultant force we determined was 6.75 kilonewtons. And this distance was 1.5 meters, which leaves this distance as 3 meters. We have our normal force, our shearing force, and our bending moment from the internal loadings when we made our section at C. So now, using our equations of equilibrium, sum of our forces in the x direction, NC equals 0, N sub C equals 0. Sum of our forces in the y direction, you have V sub C plus the 4 kilonewton force minus 6.75 kilonewtons. V sub C is 2.75 kilonewtons. To solve for our bending moment, we take the sum of all our moments about point C. You have our BY separated by a perpendicular distance of 4.5 meters minus the distributed loading resultant force, which is the perpendicular distance of 1.5 meters, minus our bending moment, M sub C. Solving for M sub C, you get 7 kilonewton meters. So now we will start talking about stress, and in particular, average normal stress. So we will assume the material is both homogeneous and isotropic, which mean the material has the same physical and mechanical properties throughout its volume, and it has the same properties in all directions. A good example of this type of material is steel. Anisotropic materials would be like wood. Which has different properties in different directions. So stress is defined as the intensity of the internal force acting on a specific plane or area we'll keep it like that. So with that being said, we know we have normal forces, shear forces, so then we can have normal stress, which would be the intensity of the force acting normal to delta A, and this is given by sigma, the symbol sigma. And we can have shear stress, which is the intensity of the force acting tangent to the area delta A. And this is given by tau. Units of stress are force over area. So in SI units, standard is newtons per meter squared. And 1 Newton per meter squared is equal to 1 Pascal. And US units, we express once again the still force per unit area. So pound force per inches squared, which we know is a PSI, pound per square inch. You can also have kilopounds per square inch, which would be kilopounds, KIP, over inch squared, which would then be abbreviated as a KSI, kilopounds per square inch. So back then to our average normal stress. We said sigma, our normal force over the area. So this would be our N, the numerator, will be the internal resultant normal force. And the A will be the cross-sectional area. This is the average normal stress at any point on the cross-sectional area. The average shear stress tau average, which is the internal resultant shear force, and this is the area of the section This is the average shear stress at the section which is assumed to be the same at each point on this section. The average shear stress has the same direction as the shear force V. So let's take a look at some example problems. Let's look at example 7.6. This is page 333 in the text. So in this problem, you have an 80 kilogram lamp supported by rods AB and BC. If rod AB diameter is 10 millimeters and rod BC diameter is 8 millimeters. Determine the average normal stress in each rod. So we need the normal force, right? The loading here. So we need to know the force in each rod. So first off, they gave us the mass of the lamp. We need to know the weight or the force. So we know that's mass times acceleration. So we'll say the weight here is 80 kilograms times 9.81 meters per second squared, which would give us 785 newtons. So we take out forces in the x direction. You have your FBC times the 4/5 leg ratio to get the x component there, right? FBC and FAB both have x and y components. Minus, since the sense of FAB is directed in the negative x direction, that's minus. And that'll be cosine to get the A leg, A over C, cosine of 60 equals 0. We have two unknowns, so we need another equation, independent equation, to solve for the two unknowns. Two unknowns, two independent equations. So in the y direction, you have your, both are pointed in the positive y direction. So your FBC times the 3/5 ratio plus your FAB times sine of 60. But we cannot ignore the weight, which is 785 newtons of the lamp. Solving these two equations either by substitution or simultaneous, substitution being easier, you get FBC 395.2 newtons and FBA 632.4 newtons. Therefore, the average normal stress in rod BC, the force over the area. Force FBC, 395.2 newtons over the area. FBC had a diameter of 8 millimeters. So the radius would be 4 millimeters. Power squared, 0.004 meters squared. Megapascals. FBA over ABA, the force over the area. The diameter was 10 millimeters, so the radius will be 5 millimeters, which is 0.005 meters squared. So that's an example of normal force. Then look at an example of shear stress. So look at example 7.8. This is page 338 in text. So the average shear stress in the 20 millimeter diameter pin at A. If you look at the small A we'll say the pin at A, the small image there, it is termed double shear, as it is supported by shear force on each of the two surfaces. The pin at B this is the pin, this is the pin. This is single shear. Okay. So the problem says determine the average shear stress in the 20 millimeter pin at A and 30 millimeter pin at B. So let's begin our work. Well, looking at it and remembering our chapter 4 skills, A is a pin, right? So we know the support reactions. We have an AY component and an AX component. We have the 30 kilonewton force here and the cable FBC. And this is a 3, 4, 5 triangle. It's the angle here. This is 4 meters and this is 2 meters. If we take our moments about point A, we can solve for FBC. So FBC times the vertical component, which would be 4/5, times the perpendicular distance, which is 6 meters, minus the 30 kilonewton force times 2 meters. You get FBC equals 0. Go to a fresh page. So we solve for that. FBC is 12.5 kilonewtons. So then, sum of my forces in the x direction. You have your FBC, we already know now, is 12.5 kilonewtons times the 3/5 ratio to get the x component of FBC minus AX equals 0. A sub x is 7.5 kilonewtons. Sum of our forces in the y direction. You have your AY minus your 30 kilonewtons plus your FBC, which is 12.5 kilonewtons, times the y component, which is 4/5. AY is 20 kilonewtons. So then for pin at A, this is our pin. Then we have the force of the beam, which is FA. But since it's double supported, double shear, remember, it's two fixed leaves. There's two shearing surfaces. So then to get our FA, which is the resultant force at A, back to our chapter 2 concepts, that is the square root of AX squared plus AY squared, which we saw for AX and AY, 7.5 kilonewtons and 20 kilonewtons respectively. This becomes 21.36 kilonewtons. Well, then if this is in equilibrium, then VA must be equal to FA over 2 because FA is equal to VA. Therefore, VA is 10.68 kilonewtons. For the pin at B, which we said was single shear, the VB is equal to the FB, or the FBC as we call it. What I mean by that is you had your cable FBC pulling this way, and it's supported by the beam, and since it's in equilibrium and single shear, then VB must equals FB. And we saw for FBC or FB as 12.5 kilonewtons earlier. So then getting to our average, so we found our forces in the pins at A and B. Now the average shear stress at A will be VA over the area A. We solved for VA, which we said was 10.68 times 10 to the 3 newtons, kilonewtons. Kilo means 10 to the 3. Over the area at A, which we said was a 20 millimeter diameter. Diameter, let's know, is circular. So it's pi over 4 times d squared. 20 millimeters is 0.02 meters. So that's 34 megapascals. At point B, the average shear stress, VB, or the area at B. So it's 12.5 times 10 to the 3 kilo, 10 to the 3 newtons, over pi over 4. The diameter of the pin at B is 30 millimeters, so it's 0.03 meters. So let's take a look at a problem. 726 in your text. This is page 342. So the supporting wheel on a scaffold is held in place using a 4mm diameter pin. First keyword, 4mm diameter pin. Determine the average shear stress. So we know we're looking for tau. If the wheel is subjected to a normal force of 3 kilonewtons, assume the pin only supports the vertical load. So if the wheel here (3 kilonewton force), so some of my forces in the y direction, right? So the pin goes through both sides of the wheel. So it looks like, let's say it's 2 leaves. We'll say this is the pin. And it has the 3 kilonewton force there. So then on both sides, we have our shear force V. So this is double shear. So then some of our forces in the y direction for equilibrium, we have 2 up being positive, you have 3 kilonewtons minus 2V equals 0. So V, the shear force, is 1.5 kilonewtons. Therefore, my average shear stress is V over A, (1.5 times 10 to the 3 newtons, kilo, over the area. It's a 4mm diameter pin, which is 0.004 meters squared. Okay, we'll end here in today's lecture and we'll pick it up next time. Have a safe day. Please let me know if there are any questions. Thank you.